Assalamu alaikum. Good morning, students, and welcome to Power System Analysis 1 course. My name is Yousef Ashraili, and I'm going to explain to you, guide you through experiment number 1 in this course. Is called synchronization of a synchronous generator with an existing power supply. This is part 1, and part 2 of this experiment is sequential switching of duplicated busbar scheme. In order to perform this experiment, we are going to use an old and special equipment we have in ECE department. It's called Power System Simulator. Very old equipment since 1986. It's still functioning well. So what I want from you is to have a cup of tea in front of you, relax, and enjoy the experiment. This is the Power System Simulator. And all components that you can see in any power system or power station are available in this simulator. So we have the generator in this side. In the other side, we have the grid. The grid is a huge system, infinite bus bar, stations connected together. And then we have a transformer after the grid and also after the generator. Then we have circuit breaker to connect this generator or this grid. We have also circuit breaker for there to connect it to the bus bar. Then from the bus bar, we transmit the power. So bus bar, we collect the power from all generators, all power stations to the bus bar. And in any power station, you have more than one bus bar. This is why we have two bus bars here in this power system. Bus bar number 1 and bus bar number 2. So we collect the power from the generator and from the grid here, which be considered as an infinite bus bar. Then we transmit the power using this transmission line over here. Transmission line number 1, and this is transmission line number 2. So this transmission line will just go and feed one area, one state, one city, and transmission number 2 to another city. And this is the load. We have different load, resistive, inductive, and capacitive load. So start with the generator and into the load. This is the power system. And then we need to, of course, we have all these meters to measure voltage, power factor, current, frequency, and all this. We call this one the running system because it is already running. The infinite bus or the grid is already there, already exists. And we can only switch on and off. We cannot control it. We cannot control, for example, the frequency or the voltage. This is fixed because it is infinite. It's a huge system. So this we call it running system. And this new generator, we're going to switch on and control its frequency, control its voltage. We call this one incoming one. And then in part 1 of the experiment, we're going to connect this new generator to this grid in a bus bar, connect them together, and do synchronization. And we'll go in details about synchronization and what is synchronization. So we have all these meters to measure voltage, current, power, and power factor, and frequency, and so on. We have also these two types of switches. We have the circuit breaker, CB3 here, CB4, CB5, and so on. And we have isolators, manual switches. And we'll explain the difference between isolator and circuit breaker in part 2 of the experiment, the sequential switching between two bus bars. We also, now for power system, we say we start with a generator, step up transformer to transmission line, and then to the load. And from there, we also have the control for the generator, how we control the prime mover of the generator, the speed and the frequency, and also how to control the excitation and the output voltage of the generator. We have here the synchronization unit, how to do synchronization. We're going to explain this one in details. And in this side here, we have what we call test points. These test points are used for these relays. These relays are for protection of the power system. We have the power system from the generator to the load, and then we need to protect this power system starting from the load back to the generator. We have different type of protection over voltage, over current, over frequency, and the voltage, reverse power to protect the generator, and so on and so forth. And all this you're going to study if you take power system protection. So these test points are used to test the protective devices if they are working fine. And we have alarming system. If there is any fault in the system, the alarm will be on, and then you can reset after clearing the fault. We have here emergency switch in case of emergency. And this is the main switch of the generator to switch on and off the power system simulator. So this is the mimic diagram, the front panel of the generator. And later on, we are going to explain in details different parts of this generator. From the back side of this generator, we have those cabinets. Cabinets number 1, 2, 3, 3 cabinets. Inside those cabinets are the equipment and components of this generator. So it is not a simulator. It's not just a simulation. It's a real generator there, real system. We have a generator, we have a prime mover, we have transformers, and we have, for protection, we have CTs, VTs, and so on. And also transmission line and load. So we're going to explain to you later on all these components inside this generator. So we're starting from the grid. This is the grid. This is MCCB, which is this one here, the main switch. Once you switch on this one, CB2 is automatically switched on, controlled by the PLC, programmable logic control. For the grid, the output of the grid, once it is on, is 415 volt. This is the voltmeter to give you the voltage output of the grid. And this system here is designed to work on 110 volt. This is why we need to step down the voltage from 415 to 110. Once you switch on, you're gonna see 110 on this one after the transformer number 2. So as I said, this is a infinite busbar Hughes system, so you cannot control the voltage or frequency of this one. You cannot affect it. It's just to switch on and off this one using circuit breaker 4 to connect it to the busbar or disconnect it from busbar. Okay. In the generator side, this is the generator, and this generator again is connected to a transformer. Normally in real life, as you know, the transformer after the generator is used to step up the voltage to a transmission level. But in our case here, since this system is working 110, we need to step down the voltage of the generator to 110 volt. 110 volt. For this generator, we measure the voltage, current, the power factor of the generator, also the active power and reactive power coming output from the generator. We need to protect the generator. We have all this protection for the generator since it is very important equipment in power system. We need a very good protection for it. We have overcurrent, we have reverse power, differential protection, all this type of protection for the generator so we don't lose it. This is the generator from the back view. And this one is the prime mover of the generator, the DC motor. In real life, the prime mover is a turbine, but we cannot have a turbine in this lab. So we just use a DC motor to rotate the generator. In any generator, we have inputs and outputs for the generator. So two inputs, two outputs. The inputs are the mechanical power. In our case, it is the prime mover, which is the DC motor that is controlling the speed of the generator. By controlling the DC drive motor, this is to switch on and off, start and stop. And this one is to control the speed of the prime mover, the speed of the DC motor. So this is the first input to the generator. And we have, of course, some meters to measure the armature and the field voltage and current of the DC motor. This is the first input, the mechanical power, the speed. By controlling this one, we control one input of the generator, which is the frequency. So one output, which is the frequency. One input related to one output. By controlling this speed from the prime mover, using the prime mover, we control the output frequency. The second input, we call it the excitation current. Excitation. This is the meter for excitation current, is a salient pole generator. And as I show you, this is the circuit breaker to protect the generator from any fault. If there is any fault in the generator that can cause harm to the generator, the circuit breaker will trip, will isolate the generator. Now, this is the second input. By controlling the excitation voltage here, or we say the excitation current, by controlling this, we can control the second input of the generator, or the second output of the generator, which is the voltage. So two inputs, two outputs. The inputs are the mechanical power, or the speed, and the excitation. The outputs are the frequency and the voltage. Controlling the speed, we control the frequency. Controlling the excitation, we control the output voltage of the generator. Once we switch on the generator, switch on and control the speed and frequency, then the transformer will step down this voltage, which is almost 220 volt, to 110. And then using this circuit breaker 3, we can connect our generator to the bus bar. Now, if we connect the grid to the bus bar, we cannot connect the generator until we do what we call synchronization, which will come in details. These are the two transformer number 1 and transformer number 2 for the grid and for the generator to step down the voltage from 220 to 110 or 415 to 110 volt. Two transformers. Now we understand the AC sources. Once those AC sources are on, we need to connect them to the bus bar in order to transmit the power later on to the load. So what is the bus bar? Now we have two bus bars in our schematic. Bus bar 1, which is the main bus bar, and bus bar 2, we call it the rear bus bar or the spare bus bar. So a bus bar is just a bar, iron bar, that where we collect all the power from all generators. So all generators are connected from the station, in a power station. They are connected to one bus bar. And then from that bus bar, we connect the transmission line to transmit the power for far distances to our load. This is some different photos for real bus bar in real life. Different bus bars. And this one is the isolated one, isolated bus bar. So in a design, we have the source, and the source is connected to circuit breaker and then to two isolators for connecting the source to one of our bus bar, the main bus bar or the spare bus bar. This is the same, this is the design one, and it's the same what we have in our simulator. So this is the source, the generator, we have the main circuit breaker, CB3, as we have in there, circuit breaker. And then after the circuit breaker, we have two isolator, isolator 1 and isolator 2. This isolator is used to connect the generator to this bus bar, the main bus bar, or we can use this isolator to connect it to the spare bus bar. Of course, we cannot connect it to two bus bars at the same time. This is why we have this bus coupler for using to share the load between two bus bars, and we're going to explain this one later on. So, as in the design, the source is connected to circuit breakers and two isolator, the same as we have in our power generator or simulator. So also the grid, one bus bar CB4, circuit breaker, sorry, one circuit breaker CB4, and then two isolators to be connected to the main bus bar or to the spare bus bar. So after the bus bar, once we connect our source to the bus bar, we have two transmission line. Transmission line 1, which is protected also by circuit breaker 7. Transmission line. Transmission line 2, protected by circuit breaker. When I said protected, is not. I mean the protection is the job of the relay itself, but this is to switch on and switch off. So if there is any fault, this relay will just send the signal to this circuit breaker to trip, to cut. So those circuit breaker in a power system, just they are like muscles in your system, in your body, muscles. So they're taking orders from relays or from the engineer in the control panel, control room, will send the signal to the circuit breaker to switch on or switch off. This is the transmission line. So in transmission line 1, this is line 1, we can choose full line or half line. Okay, depends on the distance for the transmission line. Then after the transmission line, this is three-phase transmission line, we can then connect it to the load. Now transmission line, this is the main, the view of the transmission line in our simulator. This is transmission line 1, three-phase, and this is transmission line 2, three-phase. It consists of inductor. Each phase consists of inductor, resistor, inductor. So two inductors, one resistor. This resistor is also divided to half. So if we take one inductor and half of the resistor, this is what we call half line. And if we take two inductor and four resistor, this is full line, full line. So you can figure out what type of transmission line we have. We don't have any capacitive in this transmission line, no capacitors. So we have only inductor and resistor. So is it a short transmission line or medium transmission line? Okay. Then we have the load, resistive load. This is, by the way, this is the transmission line where we use full or half. This is the switch for choose half transmission line or full transmission line. So half transmission line is one inductor with half resistor. Full transmission line, we take two inductors with the full resistor. So dark distance. This is the load, resistive load. We can connect the transmission line to the load and connect them in delta or Y. And these are the switches, three-phase. So bare phase, we can go to 1 amp, 2 amp, 4, 6. 6 amp bare phase. These are the switches to connect the resistors in parallel so that we have more current flowing bare phase. Phase 1, phase 2, and phase 3. In a simulator, they are placed on the top, on the roof there. So because you understand that the resistor, when you connect it through time, it will generate heat. This is why they place it on the top there, so to release the heat. So different resistor Once we use those switches, we connect them in parallel to have more current. Also, we have capacitive load, three-phase capacitive load. Per phase, we have 4 amp per phase using those switches. Capacitors, those are the capacitors. So we have 8 capacitors per phase. As you can see, this is for one phase, this is for phase 2, and for phase 3. So 8 capacitors per phase, different configuration to go to different currents. So we have inductive load, three-phase inductive load. We can per phase also we can go to 4 amp per phase using these switches. Those are the inductors for inductive load. This is phase 1, phase 2, and phase 3. So for per phase, we can have like 8 inductors per phase, different configuration again. We can connect them in parallel or series to generate more current. So this is the main system. This is the whole system. We have the generation, we have the busbar, transmission, and the load. In real system, in real life, we said we have the generator, then we have a step-up transformer for stepping up the voltage to high level, 132, 200 kilovolt, 400 kilovolt, and so on. And then connected to the bus bar for transmission, we call it transmission line. Then after that, we need to step down the voltage for distribution, step down using transformer. So the voltage coming to your house or the voltage going to the factory is 415. After stepping down the voltage, let's say from 11 kilo or from 33 kilovolt to 415 volt. Then we have the distribution line. We have the feeder that feeding the power to your house, to the factory, to the hospital, to the load. Then different load you have in your house: resistive load, inductive load. Inductive like ACs, like washing machine, refrigerator. All those are inductive. And resistive load, of course, in factory like motors, huge motors are inductive load. Resistive load like lightning, or your house like also water heater, and so on. So this is about the power system. Now, why we need synchronization? We know that synchronization is the process of connecting two generators or two AC sources together. In order to connect two AC sources, we need to do synchronization. We need to synchronize those two sources to have the same rules, the same system together. Okay, the same speed, the same voltage. Now, why we need synchronization from the beginning? You know that the load is not constant, it's varying. So in one station, you may need to shut down some generator for light load. You need to shut down. And then the other day, they start the factories, you need to switch on and reconnect those generators. Or you buy a new generator, you need to connect it to the network. Or you have a complete new power station. Like we have, for example, now solar renewable energy power station, for example. We need to connect it to the network. So we need to do synchronization. Synchronization, connecting two AC sources together. Now, what are the rules for this synchronization? 4 rules we have: the same voltage for the two sources, same voltage, same frequency, same phase shift, and same phase sequence. So, okay, now for synchronization rule, synchronization can be done manually in power station or automatically. The engineer can just switch to automatic, and then they can fix the voltage and frequency, and the system will detect the in phase and connect the two systems together. Or manually, the engineer can do it manually, just wait until the two systems are in phase after fixing the voltage and frequency and checking the phase sequence, and then just connect the two systems together. Now, what are the rules for connecting, for synchronization, the same voltage, same frequency, same phase sequence, and same phase shift. Voltage. Can we control the voltage of the generator? Yes, we can control the voltage of the generator by controlling the excitation current, excitation voltage, and make it equal to the voltage of the grid. Can we control the frequency? Yes, we can control the frequency by controlling the generator speed using the prime mover. So these two we can control. What about the phase sequence? We cannot control the phase sequence, but we can check if it is good phase sequence or bad. Now, what if it is bad? Can we connect the system? No, because there will be a short circuit and the system will trip. It's very dangerous. So it has to be good phase sequence in order to make synchronization. Now we can use a three lamps method to detect the phase sequence. Dark lamp, bright lamp, rotating lamp. Can we use all these rules to detect the phase sequence or not? We'll explain later on. What about the phase shift? What about if the phase sequence is no good? Can we do something? Yes, we can just interchange or change the two phases in the generator, and then we can recheck the phase sequence again. Now, same phase shift. What do we need to do? We cannot control the phase shift, but since it is rotating field, at a moment, the two generators or the two systems, they will be in phase. And then they will have a small phase shift. That phase shift will come bigger and bigger until they are out of phase. And then they will come smaller again. They will come in phase again and so on. So we just need to wait and observe, of course, until they are in phase. Once they are in phase, we connect them together. For this, we can use synchronous scope to check the frequency of the generator and the frequency of the network of the grid, and when the two systems are in phase, we connect together. We connect the two generator or the two stations together. So now we know the rules for synchronization. We have the running frequency fixed, running voltage fixed from the grid. We need to adjust this incoming frequency to be equal to the running using this knob here, the speed of the prime mover, the speed of the generator. We need to fix this voltage of the incoming to be equal to the running using the excitation knob. Then we have the phase sequence. We'll come to the phase sequence. We have this synchronous scope. This synchronous scope here is detecting the frequency of the running and comparing it to the frequency of the incoming. So using the synchronous scope, you can figure out which one is running faster with a high speed, which frequency is higher. So if it is rotating this way clockwise, for example, then you understand that the generator has higher frequency than the grid. If vice versa, if counterclockwise, then the grid has higher frequency. If it is rotating in high speed, it means the difference in the frequency is very high, or if it is rotating in very low speed, it means that they are nearly equal. The frequencies are nearly equal. Also, you have this plus and minus sign, which means that if the pointer is inside this area from plus and minus, the phase shift between the three phases is small, and the machine can handle that phase shift. So even if you try to synchronize within this area from plus to minus, it means that the machine can bring into synchronization. So even if there is a small phase shift, the 12 sign here, it means if the pointer is there, it means that the phase shift is equal to 0, and this is the best way for synchronization, is to wait until they are in phase so that no circulating current is there. Now, between plus and minus, there will be a circulating current, but it is very small. Now, the out area here, if the pointer is in this area, it means that the phase shift is very high, and if you try to synchronize in this area, the system will trip, because high circulating current will just flow to the generator and it will trip the generator. So this is about the phase shift. We can use the synchronous scope to detect the phase shift and see when the two systems are in phase and connect them together. What about the phase sequence? Now for phase sequence, as I said, we have the three lamps method. Now, before we go to phase sequence, let's see what are those methods: dark lamp, bright lamp, and rotating lamp. Now, we know that the lamp will be on if current pass through it. And the current will pass if we have a voltage difference across that lamp. So now in AC, the lamp will be on, the current will pass if we have voltage difference or if we have phase shift as well. So even if the amplitude here equal to this amplitude, but we connect, instead of the red phase, we connect yellow or blue phase, even if the amplitude is the same after adjusting the voltage to be equal, but they have a phase shift of 120 degree, then that phase shift can cause the current to flow and the lamp will be on. Considering that, check this connection now. We connect red and red phase across the red lamp, blue and blue phase, red, yellow and yellow. So let's have the system when it is in phase. The voltage equal, the system in phase, the two sources are in phase, then what will happen? The amplitude the same, the phase shift equal to 0 because the red with the red, so no phase shift. Phase shift equals 0. It means that this lamp at that instance when they are in phase will be dark, as well as the blue and yellow. This is why we call this one dark lamp method. Dark lamp method means when the two sources are in phase, the lamps are going to be dark, and then we can synchronize the two systems when those lamps are dark. Even if we don't have synchronous scope, we can depend on the dark lamps. Now, let me show you an example for that one. System is running. You can see when it is out, the lamps are bright. When it is in phase, you see when it is in phase, they are dark. Out of phase, they are bright. So they are going dark and bright together. So the main important is when it is in phase, the two systems are dark. What about bright lamp method? So this is about dark lamp. What about bright lamp method? Now, bright lamp method, we connected so that for one lamp, it has two different phases. So the red lamp, we connect the red with the yellow, for example. The blue lamp, we connect blue with red. The yellow lamp, we connect the yellow with blue. So different phases across the lamp. Now, when the two sources are in phase, what will happen? The amplitude is the same. So amplitude is the same, fixed, or the same, sorry. Now, what about the phase shift? Is there any phase shift at that instance? Yes, there is a phase shift equal 120 because two different phases. Now, that phase shift will cause current to pass and this lamp will be on, right, as well as this one and this one. So at instance when they are in phase, the lamps are going to be bright. And for that one, we can synchronize when all lamps are bright. Let me show you when the system. So you can see now, if the system is in phase, the two sources are in phase, lamps are bright. If out of phase, it is dark. Okay? The lamps are dark. So it is vice versa. What about the third method, the rotating lamp method? Rotating lamp method means one lamp is connected at the same phase, so red to red. If we choose this one to be dark, you know that if it is red to red, then when they are in phase, it will be dark. And the other two, we connect two different phases. So red with yellow and yellow with red, yellow with blue and blue with yellow. So what will happen if they are in phase? The amplitude is the same. This one has no phase shift because the same phase, so it will be dark. This one, the amplitude is the same, but it has a phase shift between the yellow and blue, so the current will pass and this will be bright. This one also, the amplitude is the same, but phase shift equal 120 between yellow and blue, so this will cause the current to pass and this will be bright. We call this one rotating. Why rotating? You know that it is rotating field. At the instance it will be in phase, and then it is out of phase, phase shift, in phase, and so on. So at this rotating, this will be dark and bright. When this one is dark, those are bright, and then this one is bright, those are dark, and so on as rotating. We can synchronize when the red is dark because it is connected in the same phase, and these two are bright. Let me show you. So you can see this is dark, these two are bright. Check at this instance when it is in phase, dark, bright. So dark, bright. Okay? It's very clear. So now let's start the experiment. We'll switch on the system, adjust it, prepare it so that we can synchronize the generator to the grid. First of all, we press the start button to start the DC motor. And while the system is on, before we adjust the speed, let's see the readings for the running system. The running system is on. The frequency of the running system is 49.99, and the amplitude of the running system, the voltage is 110 volts. So you need to record this one, you need to write it down in your result sheet. VR 49.99 and FR is 49.99 and VR we running is 110 volts. Let's continue now. So we adjust the speed of the generator so that the frequency is equal to 50 Hertz. Frequency should be equal to 50 Hertz. Now, what should be the speed of the generator and why we adjust it to 1500? There is a relation between the frequency and the speed. For the generator with number of volts. So this machine, number of volts are 4 volts machine. Since it is 4 volt machine, if the frequency we needed is 50, then the speed should be 1500. This is why we adjust that to 1500 using the speed. Let's continue. Now the second input is the excitation knob. We need to adjust the excitation, but before that we need to switch on circuit breaker 1, which is protecting the excitation, and adjust the excitation so that the output voltage of the generator equal to the voltage of the running system, which is 110. Now you can see the frequency of the generator is almost 50.11. And this is the frequency of the running system. This is the amplitude. So now you need to record this one down. Record the amplitude V running equal 110, F running equal 50.01. Record it in your result sheet. And the incoming VI equal 110 as well, and FI is slightly higher. Let's continue. So Fi equal 50.18. Record this value, 50.18, slightly higher than V running. Now, why this one? Why the frequency of the incoming is higher than the frequency of running? We need this frequency of the generator. The frequency of the generator, we need it to be slightly higher than the frequency of the grid, so that when we synchronize the two systems, the current will flow from the generator to the grid. And the grid is a very huge system, it can handle that current. While the generator, if this one is the frequency of the grid is higher, the generator cannot handle the current flowing to it and it will trip. So now you can see the same voltage, the same frequency. This one is slightly higher, of course. We need that one. Now you can see the lamps. This is they are almost in phase with the small phase shift. The lamps are dark because we are using dark lamp method. Let's continue and see while this one is rotating. The lamps will go to bright when they are out of phase, and then when they are in phase, they will be dark. Let's continue. So now out of phase, lamps are bright. When it's going to in phase, it is dark. Is the phase sequence good? Yes, because the lamps are going bright and dark together. This is the indication for phase sequence. Phase sequence is good because the lamps are going dark and bright together. Now we just wait until this one is in phase, and then we synchronize the two systems together. See now? We just wait until this one in phase and we close CB3 to synchronize the two systems together. Now the system is synchronized. The lamps will stay dark because it is dark lamp method. Frequency now will be equal, the same as the frequency of the grid, as well as the voltage will be the same as the voltage of the grid. As you can see, the voltage will not change, the frequency will not change. Synchronous scope will stop because it is synchronized now, and the lamps will just remain dark. The two systems are synchronized. Now, the question is, after synchronization, now the two systems are synchronized. After synchronization, what will happen if we increase the speed of the generator? We know before synchronization, increasing the speed will increase the frequency. But the frequency now is fixed because the two systems are synchronized. We cannot change it now. And what will happen if we change the excitation? No. Before synchronization, the voltage was increasing. But now we cannot change the voltage. The voltage is fixed because of the synchronization. So after synchronization, what will happen? What will increase in the output of the generator if we increase the speed and if we increase or decrease the excitation? This question, you need to answer it. Let's do it one more, and this time is called bright lamp method. You see the bright lamp connection, red with blue, blue with yellow, and yellow with red. We adjust the voltage, the same 110, we adjust the frequency, this is slightly higher as we need that one. And then we are going to wait for the synchronous scope until they are in phase. We'll close CB3. CB4 is already closed because the grid is already connected to the bus bar. We just need to close CB3 in order to connect the generator as well to the bus bar. Let's see how to do that. Wait till are in phase and close it. So now we just wait until they are in phase and then we close CB3. The two systems are connected together, synchronized, and you can see the lamp situation. They are bright because we are using bright lamp method. The same situation but with rotating lamp method. rotating lamp method, you can see red with red, this will be dark. This one is blue with yellow and yellow with blue. So what will happen in this case? We also adjust the voltage using the excitation. We adjust the frequency using the speed knob. And so the excitation using, we adjust the voltage using this excitation. We adjust the frequency using this knob here for the speed. And as you can see, connection for rotating lamp method. So let's wait until the synchronous scope is in phase. The two systems are in phase, and we'll close CB3 to connect the generator to the grid, which is already connected to the Busbar. Okay. So the two systems are synchronized. Two systems are synchronized now. This is closed. You can see that the red is dark, the blue and yellow are bright because we are using rotating lamp method. So we'll come to the same question, and now you answer that question. What will happen after synchronization and before synchronization? Before synchronization, if we increase the speed, the frequency will change, will increase. If we increase the excitation, the voltage will increase. Now, what will happen after synchronization? Now, to make it clear for you, uh, imagine that you join a team, and let's say football team, and that team is wearing a blue shirt. Now you don't like blue shirt, but you have to wear it when you join the team. So after joining the team, you cannot wear, let's say, yellow shirt because you like it. No, you have to wear the same shirt as the blue shirt for the team. So the team here, the grid, they said for this generator, if you want to join us, you have to have the same voltage and the same frequency. Now the generator accepts to have the same voltage and the same frequency to join the team. So after synchronization, after the team accept the generator to be one, to join them, what will happen now if we increase the excitation or if we increase the speed? Now don't forget that the voltage and the frequency are the rules for joining, so they cannot be changed. You cannot touch them anymore because now is not a single player. The generator now is playing with a team. So generator itself cannot change its own frequency or voltage. But what will change? If you remember, we explained this one from the beginning of the experiment. We said if the generator is connected to a load, then if we increase the speed, more current will flow from the generator, and we increase what type of power? Is it P or Q? Now, if we increase the excitation, which power is increasing? Is it P or Q after synchronization? Okay, this is about part one of the experiment, the synchronization of a generator to the grid. Now, part two of the experiment will be sequential switching of two bus bar. So now the synchronization is done. Let's go to part two of the experiment, sequential switching of a duplicated bus bar, sequential switching of the load between two bus bar. Now, in order to understand this part of the experiment, you need first to ask yourself these questions. You need to know the answer to these four questions, let's say. What is the bus bar? And we already answered this question. Now, why we need more than one bus bar in a power station? You need to understand this. Also, what is the difference between circuit breaker and isolator? What is the difference between them? Also, what is the order of switching between this isolator and circuit breaker in a live circuit? Let's say that for this load, for example, let's say that this load is live. So, and we want to switch off, we want to cut the load. Which one is to switch first? Is it the circuit breaker or isolator? Which one is to be opened first? Let's say that this load is not connected and we want to reconnect it to the system, let's say to the main or spare. So which one to be closed first? Is it the circuit breaker or the isolator? You need to understand all these questions. And this is the system that we are going to use. Two bus bars, the main bus bar and the spare bus bar, or let's say the front and the rear bus bar. The voltage will be 110. Two loads, they are the same, 4 amp resistive and 2 amp inductive load for two feeders. We have also the bus coupler if we want. This is used in case we want to share the load between two bus bars. This is what we talk about when we have two bus bar scheme. Then we have generator, for example, or even many generators, or this, let's say the grid is synchronized with the generator. All these are connected to one bus bar. So the load, the generation is connected to one bus bar only, either connected to the main or to the spare. Okay, but let's say that we want to share the load between two bus bars. It means that we want these two bus bars to be on, to be live at the same time. So this is where this bus coupler is coming, the job of bus coupler. So bus coupler is only used if we want these two bus bars to be live at the same time. They can be connected using bus coupler, and you will see how to use that. Okay. So in our simulator, these are the two bus bars. This is the main bus bar or the front bus bar, and this one is the rear bus bar or the spare bus bar. We are going to connect the grid to our bus bar. As you can see, we are going to connect it to the main bus bar. This is on to the main bus bar. Okay, so the main bus bar will be live. The spare bus bar or the rear bus bar will not be live. Now we are going to use CB4 to connect this grid to the bus bar. CB3 will be open. We are not going to use the generator. Okay, we'll just switch off the generator to avoid noise only. But we can, of course, synchronize the two systems and use sequential switching while these two systems are synchronized. Okay. Now we have two feeders. This one with a load 4 amp resistive and 2 amp inductive. Now this feeder here is, it has two isolators. This isolator to connect the load to the front bus bar, and this isolator to connect it to the rear bus bar. So these two isolators, they cannot be on at the same time, because we said that the load can be connected to one bus bar only at the time. So this one can be on and this one off, or this one on and this one off, or they can be off together, but they cannot be on at the same time. And then we have a circuit breaker to protect the circuit. Also in this left feeder, we have two isolators to connect this load. We are going to connect also 4 amp resistive and 2 amp inductive. And if we want to connect this feeder, this load, to the front bus bar, we are going to use this isolator over here, while this one will be off. If you want to connect it to the rear bus bar, then this one will be on while this isolator is off. So this is what happens. Now, we said that the grid is connected to this bus bar, to the main bus bar, while the rear bus bar is off. Now, if we want two bus bar to be on, so we need to use the bus coupler. This is the bus coupler. And bus coupler is protected by two isolator and one circuit breaker. So this is the main purpose of this bus coupler. Now we already answered the question of what is the bus bar and why we need two bus bars in power station. Let's come now to the main questions. What is the difference between this isolator, this switch, and this switch? We call it circuit breaker. What is the difference between circuit breaker and isolator? Both of them are switches. Both of them, they can cut or switch on or switch off the load. Okay. Now, one difference between them is that the isolator is a manual switch. You have to be there to switch it on and off yourself. It's just manual. While the circuit breaker is automatic switch. Okay. So this circuit breaker can receive a signal from the relay if there is abnormal condition and switch off tripped circuit, or from the operator in the main room, okay, control room, to switch on, like CB3 for example. What we did, we send the signal to the CB3 to synchronize the two systems, so to close or open CB3. Okay? So this is one difference, but the main difference is for the safety of using this isolator. Since isolator you have to do it manually, let's say that you have an iron at your house, and that iron, the wire is loose, and you want to switch on and off the iron. Okay, once you switch on and off, you will observe that there is a spark inside happening, a spark, small spark. Now let's say you want to switch off the power that is entering your house, which is, let's say, 300 amp, using a manual switch which you have in your house, 300 amp. Let's say you want to switch off 500 or 1000 amp manually. So it's not a spark anymore. It's what we call flash over. Okay, this is why you cannot never use manual switch or isolator in a live circuit. You cannot use isolator in a live circuit. Okay, if in case they have to do it, they are doing it with a stick in a high distance. They are not doing it while they are closing or nearby that switch. Okay, and you can see some videos about that, switching off load in a live circuit. I think this is the name, and you can see in YouTube. Now, why it is safe to use this circuit breaker in a live circuit? Because the switching part of a circuit breaker is inside enclosure. Okay, one thing is that you can of course switch on remotely, but the main thing is that the switching part is enclosed inside enclosed, and they are putting material inside to absorb that spark, like for example SF6 or oil vacuum clean, or oil or vacuum circuit breaker. So whatever the name of the circuit breaker, it is the thing that they are putting inside to absorb that. They said, for example, SF6 circuit breaker. So there is an SF6 oil inside the container. Okay, that is the circuit breaker inside. So absorb that. So this is why it is safe to use circuit breaker to cut a live circuit, but it is not safe to use isolator. Now the last question is, what is the order of using isolator and circuit breaker in a live circuit? Let's say that we have a load here, and that load is on, CB8 is on, and it is connected to the front bus bar. So this isolator is on. Let's say I want to switch off this, and let's say that the current is 100 amp or higher. Can you use isolator to switch off? No, we cannot use isolator. It's not safe to use isolator. So if it is on, you want to switch off, the order of using off switching is circuit breaker first and then the isolator. Okay. Now let's say that this one is off and we want to connect it to the system. So which one to switch first? Is it the isolator or the circuit breaker? So that is vice versa now. We have to start with isolator first and then the circuit breaker. Because if we switch on the circuit breaker and when we come to isolator, we cannot use it because high current will pass and flash over will occur. So in live circuit, we use circuit breaker first and then isolator. This is the order of switching. In a dead circuit, if we want to switch on, we use isolator first and then the circuit breaker. Okay. Now the next step is left feeder transfer. This is the situation now. What we have that the main is connected to sorry, the grid is connected to the main, and this load, this is the left feeder, is connected to the main, as you can see, and the right feeder, which is 0.3 kilovolt amp, is also connected to the main. All of them are connected to the main, and the bus coupler is open. Now this is the situation. This is what we need to do. The right feeder, which is protected by TB8, is the same, connected to the main. We don't change it. The left feeder, we need to shift it to the rear bus bar or the spear bus bar. In order to do this, we need to bring this spear bus bar to life. It is off now. So we need to use the bus coupler. We need to close these two switches in bus coupler, and then we close the circuit breaker. Now we need to perform this circuit. Let's see how to do it. Okay, so first of all, these two now are connected. So first step is to close. Now first step is not to shift the load, but to bring this bus bar, the rear bus bar, to bring it to life. We need to give it power using the bus coupler. So close two isolators first, and then next step is to close the circuit breaker. Okay. Then this bus bar, the rear bus bar now, which is protected by CB7, is close to the main, is connected to the main. We need to shift it. So it is live now. We cannot use the isolator. We need to use the circuit breaker first. Switch on the circuit breaker first, and then we can switch on the isolator and take it. Now it is not live. We need to connect it now to the rear bus bar. So we start from isolator and then the circuit breaker. So if it is live, we start from circuit breaker and then isolator. If we want to switch it on, we start with isolator first and then the circuit breaker. Now you can see that the front, or sorry, the right feeder, this right feeder is connected to the main, while this left feeder is connected to the rear bus bar. Okay? This is what we call sharing load. Next is the right feeder transfer. Right feeder transfer. So this is the situation. We need to return back the left feeder to the main. Right feeder is also connected to the main, all of them. Bus coupler is connected, so two feeders are on. Now we need to shift the right feeder. So we start with circuit breaker to cut the load first, circuit breaker, and then we connect this isolator so that it is connected to the rear feeder. Let's see how to do this. Right feeder transfer. Now both of them are the front, sorry, the right feeder is connected to the front bus bar, and the left feeder is connected to the rear bus bar. So first, before we start with the right feeder, let's shift the left feeder first to the front bus bar. Let's shift it back to front bus bar. Since it is live, we start with the circuit breaker first, and then the isolator. So first with circuit breaker and then isolator. Then we connect it back to the front bus bar. We start first with isolator and then finally the circuit breaker. Now it's connected to the front bus bar, the main bus bar. Let's see how to do this now in the right feeder. So the right feeder is now connected to the, you can see the right feeder. This is the right feeder. Now is connected to the main bus bar. So it is live. We cannot shift it now to rear bus bar. We have initially to switch it off using the circuit breaker CB8, and then we can shift it to the rear bus bar using C43. Okay, let's see how to do this. So start with the circuit breaker. then the isolator. Now we connect it to the rear bus bar. Okay, so now you can see that it is connected. It is connected to the rear bus bar. So once we switch off, we can now use the isolator, and then finally the circuit breaker. Don't forget the order of switching between isolator and circuit breaker. So by the end of this part, some discussion so that you can figure out the results and write them down in your answering sheet. This is step 5. Load feeder on left, load on left feeder, load on right feeder, and load on front bus bar. You have to use this figure here. Don't forget the main is the front bus bar, the spare is the rear bus bar. So as well for this one here, step 8, the load on, or the total load on front bus bar, the total load on rear bus bar, depending on this situation here, or this figure. And finally, step 18, the load on front, the load on rear. Front is the main, rear is the spare bus bar, depending also on this figure over here. This is what we did. So you can figure out the results of the load from this one. Thank you very much. Enjoy your time. Stay safe. Stay home. If you have anything, any questions, you can contact me or contact Dr. Amr through the email. Thank you very much.